A wave is defined as a disturbance that transfers energy through matter or space. There are several types of waves, but for this video we will focus on wind-generated waves. Wind-generated waves are created by friction between wind and water on the surface. When wind blows over the ocean surface, it pushes down on and parallel to the surface. This causes wind to pile up into small waves known as ripples or capillary waves. The development of waves in deep water may be attributed to three primary factors: wind speed, duration of wind, and the fetch of wind. The fetch of the wind is the distance of open water surface across which the wind blows. Swells are long-crested, uniform, symmetrical waves that are created when wind speeds diminish and waves move faster than the wind. This causes the steepness of the wave to decrease. Swells have traveled out of the area which they originated. They move with the minimal loss of energy over large stretches of the ocean surface, which allows them to transport energy away from one area and deposit it in another. Waves at a shoreline are still present when there is no wind because of the movement of swells to distant areas. This is an animation showing circular orbital motion. In a wave, the water itself does not travel the entire distance, but the waveform does. The wave moves in a circular orbital motion in which the water passes energy along, allowing the wave to travel long distances. This image of a floating rubber ducky shows circular orbital motion. As a wave passes from left to right, the motion of the floating rubber ducky resembles that of a circle. This is what's known as circular orbital motion.
A wave is determined by the ratio of the water's depth to the wavelength of the wave. Deep water waves move in a circular orbit, while molecules in shallow water waves move in an elliptical orbit. When the depth of water is much greater than half of the wavelength, then the wave is classified as a deep water wave. In deep water waves, the wave speed is a function of the wavelength. When the depth of the water is much less than half the wavelength, then the wave is a shallow water wave. In a shallow water wave, the wave speed is a function of water depth. A deep water wave turns into a shallow water wave when the depth of the water becomes less than 1/2 of the wavelength of the wave. When a wave has some characteristics of a deep water wave and some characteristics of a shallow water wave, the wave is classified as a transitional wave. The wavelengths of transitional waves are between 2 and 20 times the water depth. The speed of transitional waves depend partially on water depth and wavelength. As a wave enters shallow water, it decreases speed. The wave behind it still has the original speed though, so wavelength decreases as the wave in the back catches up to the wave in the front. At this point, the energy must be displaced elsewhere, so the wave height increases. This increase in wave height and the decrease in wavelength cause an increase in wave steepness, which is height over length. When the wave reaches a 1:7 ratio of height to steepness, the wave will break. There are 3 types of wave breakers. The first is known as a spilling breaker, which are caused by a gently sloping beach. This happens because the wave gradually loses its energy after a long expanse and makes the break have less energy as well. The second type is a plunging breaker, which is caused by a steeper beach when the crest outruns the wave. The last type is a surging breaker, which is formed by the steepest, most abrupt beaches. Since the ocean floor comes up so suddenly, the wave loses energy over a very short period of time and breaks at the shoreline.